Welcome to Introductory Chemistry with Dr. H. This is a video about colligative properties of solutions, particularly freezing point depression. So very briefly I'm going to talk about colligative properties and then talk about freezing point depression and the molal freezing point depression constant. So when we're talking about freezing point, what we're thinking of in a solution is, or in a pure solvent, is molecules or atoms moving from the liquid phase into the solid phase. So the solid phase is this fixed lattice of the atoms or molecules, and they don't move relative to one another. In the liquid, there are still strong intermolecular forces holding those molecules in the liquid, and they're constantly having intermolecular forces, but they have mobility to move past one another and tumble around. Once they're fixed in the lattice, they no longer move. And so as you take a pure solvent below its freezing point, what happens is it becomes favorable for the molecules to succumb to the intermolecular forces of their neighbors and to lock down into the lattice. So, we think about what's happening is one of these water molecules or one of these solvent molecules is going to be moving around, and then all of a sudden it's going to get cold enough, it loses enough kinetic energy that all of a sudden it locks down into that lattice. And then, another molecule is going to have the same freedom, and it's eventually going to lock down into the lattice. And really, crystal lattices are pretty particular for only like molecules. So if this were water freezing, there's a lattice of water that's sitting there, and at the surface of that lattice are spaces that are just right for another water molecule. And so what we tend to see is that crystals tend to be very pure materials because they have little spaces in the lattice for other like molecules. So what happens when you make a solution, the colligative property, it really doesn't matter what the other molecule is, the solute molecule in that solution. That solute molecule isn't going to fit into the lattice. So say, for example, we have gray molecules mixed in. These gray molecules are also moving around, and as they lose kinetic energy, they're going to bump into the lattice, but there's not a spot for them in the lattice. They don't fit in the lattice, so they're just going to bump back out. But then it's still there, and it's going to bump into it again. And every time it bumps into it, it's taking up a possible space where a solvent molecule might find its way around, right? So this solvent molecule is also looking for a spot as the kinetic energy goes down. And it takes more collisions, it takes more time. You have to lower the energy more to make that process favorable because there's sort of some blocking interactions between the non-solvent molecule, if you will, and the solute molecules. The solute molecules are blocking the spaces for solvent molecules to come down. So the observation is you actually have to cool a solution to a lower temperature in order to get it to freeze. And there are lots of sort of important implications of that. But let's just stick with that principle for a moment. So what that means is the temperature of freezing goes down from the pure solvent. And we can quantify that using this equation. And the equation is simply the change in the freezing temperature, delta TF, is going to be related to this molal freezing point depression constant. And it's really important to remember that this is for the solvent, not for the solute. It doesn't matter what the solute is. It's for the solvent. So the more solvent in there, the more the temperature is going to be depressed. But this constant refers only to the solvent itself. So if this is water, the molal freezing point depression constant for water is 1.86 degrees Celsius for every 1 molal the solution is. So if you made a 1 molal solution, that molal could be one substance or any substance as 1 molal. So 1 molal is 1 mole of some solute per kilogram of solvent. So for every molal, the temperature goes down by about 2 degrees, 1.86 degrees. So you can really dramatically affect the freezing temperature of a liquid by adding some solute. And this is what happens when we put salt on the roads in the winter. What we're doing is we're adding particles to the water, right, to prevent it from freezing because it has to be so much colder to actually freeze if you add a high concentration of some solute like salt, for example. And so there we are. So you can calculate this. So if you know the molality of a solution and you know the molal freezing point depression constant, you can calculate the change in temperature, right? And it's this T freezing 0, that's the normal freezing point, so 0 degrees for water, and then you're going to get a lower freezing temperature, and so the difference between the new freezing temperature and the actual, the pure freezing temperature is that delta T. So I hope you found this video useful about freezing point depression.